love to leave this planet? Raise your hand.
Wow, that's a lot.
Luckily, there are some opportunities coming up. There's Mars 1, where you can go to Mars, but without a return ticket.
And who applied for this one? Do we have any applicants for Mars 1 in the hall? Whoa, more than we expected. 3, 4.
So just a few, but brave. SpaceX?
But recently also SpaceX announced their detailed technical plans on how to get to Mars and their technical plans for the vehicle. Who has seen the announcement? Raise your hands, yes.
Okay,
Whoa.
Quite some people are informed. So since we already know there's 3 or 4 people who would go to Mars without coming back, who would trust his life to Elon Musk and go up there with him? Some more, yeah. I definitely see a colony up there.
Okay, by the way, what's the difference between the Berlin airport and Mars? Humans will land on Mars in the foreseeable future.
The next talk is not only about Mars. It's about the 3,518 known exoplanets and how to pick the right one for a civilization attempt.
And we'll also learn about how to get there and what technology need further research.
Because as you know, it's not about the target, it's about the journey.
Liz George and Peter Buschkamp, who have both provided us with food for thought on prior C3 events, are now here for us on this stage.
They have many things in common. They are both instrument builders for astrophysics. They both work at the Max Planck Institute for Extraterrestrial Physics, and they are both working in the same infrared group.
And on top of that, they both develop some of the world's most sensitive infrared instruments.
Please take us with you on a journey through space. Liz and Peter.
So, hi everybody. It's great to be here. I think this is by far the biggest audience that either of us has ever spoken in front of.
The biggest one.
Yeah, the biggest one. So, thanks for coming out.
Thank you.
So today we want to tell you about interplanetary colonization and by extension, interstellar colonization, which is much harder. So we'll start out with the question, why leave Earth? Earth is a pretty great place, right? So this is our home planet. It is about 70% surface area covered in water, as you heard in the last talk. It's got a convenient 1 g of gravity, 1 bar of atmospheric pressure. The atmosphere is about 20% oxygen.
And don't forget the most important part.
Oh yeah, it's the only planet we know of that has Wi-Fi. So, Earth is pretty great. Why leave it? And we can start with analyzing the past history of Earth, namely that Earth hasn't always been such a great place to live. So this is the fraction of species to go extinct in each time interval as a function of time. So this goes back about 550 million years. And there's a lot of spikes on this plot, 5 of which are known as the Big 5 extinction events. And you may have heard of some of these, one of which, the most latest one here is when all of the dinosaurs were wiped off of the planet. So something else you might not know of is that we're in fact in the middle of the 6th big extinction event on our planet, where we're losing species at a rate 1,000 times above the background. So we can ask ourselves, what has caused these extinction events in our Earth's history? There's many things. So the first big extinction event was because we actually had too much oxygen. Extinctions also happened due to too little oxygen, volcanoes, sea level changes, global warming, global cooling, giant meteors hitting the Earth, and most recently, human activity. Okay, so you can say, you know, we're actually much more advanced than the dinosaurs. We have technology. In principle, we should be able to survive any of these planet-altering potential extinction-causing events that come our way. But actually, in the very long term, we have a bigger problem, and that is our sun. So eventually, our sun will use up all of its hydrogen fuel and balloon up into a red giant. So first, all of the water will boil off of the Earth. That won't be pleasant for anyone. And then eventually, the star will grow so large that it actually envelops the Earth inside of the star and completely fries the planet. So given that this is CCC, you can think of it as, making an offsite backup of humanity before your server room burns down, which in this case...
And in the cloud and beyond.
Yes. In this case, we know it will. So we actually have a pretty strong motive here to get off of our planet in the foreseeable future. So that brings us to our next question, namely, where are we going? So all of you in the audience and our previous speakers have talked about Mars, and we also want to know how we learn about our new home. So this is what Mars looks like from space. And you can think this is a good target for us. It's relatively close in terms of interstellar space. If you want to get an idea of distances, stick around for the last talk in this track about how space really is huge. And you heard from Jan Warner, it'll take about 2 years round trip there and back. So Mars also has an atmosphere, but it's very thin, mostly CO2. It doesn't have a magnetic field, so it's constantly bombarded by cosmic rays and solar wind. So this essentially sterilizes the surface and means that humans would have to live underground. It's also pretty cold there. So while Mars is close and technically is in the habitable zone of our sun, meaning there can be liquid water on the surface, it's not actually that comfy of a place to live. Another target that people talk about is Europa. So this is one of the moons of Jupiter. There's several of them. And this has been a very interesting target because it's actually an ocean world. So the entire moon is covered in water with a very hard, thick ice shell on the outside. And conveniently, it also has an atmosphere of almost pure oxygen. So you think, great, it's got an ocean, it's got oxygen, what more could we want? Unfortunately, the average temperature on the surface is so cold that the ice is as hard as granite, and you'll have to drill through 15 kilometers of it before you get to the ocean. It's also sitting in Jupiter's radiation belts, so the radiation intensity on the surface is so high that a human would die in less than 12 hours. So also not so pleasant.
And also the monolith tells us not to land there.
That's true. Okay, but the really interesting thing is these planets are close, and we actually know an extraordinary amount about them. And the question is, how do we know these things? So in our solar system, we can actually send satellites to orbit the planets and landers that sometimes crash, but sometimes actually land there and give us some information. So this is a picture of a mountain. It's Mount Sharp on Mars, and it's actually taken by the Curiosity rover that is sitting there on the planet right now taking data. So this is a selfie Curiosity took of itself. And one of the really cool things about Curiosity is it's got a giant laser on it that it uses to actually vaporize the rocks and analyze them. So we have this probe sitting there, and this is the first spectrum to come out of this rock vaporizing laser measurement device. And what you can see here is a whole bunch of spikes in the spectrum. And each of those, if you have some very good chemists back home, can be matched to different elements. And so you can see our soil on Mars has iron, magnesium, silicon, aluminum, calcium, etc. All things that would be very useful to, say, potential habitants of Mars, or just in general to know about what kind of life could live on Mars.
So Liz, you are essentially saying we are safe in growing potatoes now.
Yeah, we could grow potatoes in this,
Good.
for example. Okay, so again, this brings us back to our previous problem, though, of the sun is eventually going to envelop the Earth and make Mars a hellish desert world. So we got to go a little bit farther than Mars. And that brings us to exoplanets. So this is a graph of the exoplanet detections per year since the 1980s. And you can see, 30 years ago, we didn't even know that there were other planets in the universe other than in our solar system. And in the last several years, we've really learned about an explosive growth of exoplanets. Well, they were there all along, but our detection technologies got better. And they're detected in many different ways, but today I'm just going to tell you about 2 different ways they're detected via the radial velocity and the transiting method, since most of our exoplanets were detected that way. Okay, so the first thing you should know is that a planet doesn't orbit a star. So rather, a planet and a star both orbit the common center of mass between the system. So in this graph, you see the big thing is the star, the little thing is the planet, and the star is wiggling back and forth. And what this means is if you're observing the star as it moves back and forth, the light is Doppler shifted throughout the orbit, and what you get is you get slightly blue shifted light on one part of the orbit and red shifted light on the other side. And if you observe it for a very long time, what you see is a periodic signal. And you can analyze this periodic signal to learn about the mass of the planet that's orbiting, how long the planet's year is, and how far it is from the star. So this is a very precise way to detect planets, but you need an extremely precise spectrograph. And this has been done in different ways over the years. Early attempts used vats of boiling hydrofluoric acid to calibrate the spectrograph. Wasn't so great for the instrumentation. These days, people use laser combs. Stick around for the next talk if you want to learn about lasers. So the other way that we detect exoplanets is the transiting method. So this is the method used by the Kepler spacecraft. And basically what you do is you just stare at a whole bunch of stars for years. And you wait for the planet to go in front of the star. And you would see a very slight dip in the brightness that will change over time. And an Earth-like transit of a planet lasts about 13 hours and happens once a year. So on average, you need 4 of these transits to define an orbit. And so it takes many years of observing before you get the exoplanets. So what you get from this, in contrast to the previous method where you get the mass of the planet, you get the radius of the planet. So you know how big it is, but since you have no idea what it's made of and how dense it is, you don't know how much it weighs. But what you can find from this system, if you know about your star, how much light it outputs, is you can define a habitable zone where the surface of your planet could have liquid water. And what you can do is you can take the orbit and the size, and you can get a good idea of, roughly what the planet's system looks like and whether the planet is in the habitable zone. So this is an example of the first roughly Earth-sized planet located in the habitable zone of a red dwarf. And the reason the orbit is smaller in comparison to our solar system, so this is the F orbit, and that's roughly comparable to the orbit of Mercury, is because the red dwarf star is dimmer. But that brings us to the next question. Okay, so we know it's a roughly Earth-sized planet, and it's sitting in the habitable zone, but does it have a breathable atmosphere? Does it have a greenhouse effect that might make it warmer? How do we find this out? And the problem with studying planets around other stars is that they're super faint. So there's actually a planet in this image, and if I hadn't put this label here, you probably wouldn't be able to tell where it is. And in fact, this is a planet that's sitting super far out from its star. It's way past the orbit of even Neptune. And if you wanted to observe an Earth-like orbit, it would be way in here. And it's roughly a factor of 1 million fainter than the star. So digging out the signal from behind the star is extremely hard. And one thing you should know about telescopes is that the bigger they are, the smaller this diffraction pattern is. So if you make a bigger telescope, you concentrate the starlight closer in, and in principle, you can see these smaller orbits. So this here is the Kepler satellite. That is what has actually detected most of our exoplanets in the universe that we know of so far. And soon, NASA will be launching JWST. It's a factor of roughly 6 bigger, so that's great. And actually, the Europeans are planning to build something called the Extremely Large Telescope. Not a joke, that's actually the name. But it will have a 39-meter dish, and this will enable us to directly study exoplanet atmospheres, with the hope being determining whether any of these habitable planets actually have an atmosphere that would be conducive to humans colonizing the planet. So I'll end my section with the Kepler Ori here. And this is all of the known exoplanets from the Kepler mission in their orbits to scale. So the bigger planets are Jupiter-sized and the small ones are Earth-sized. And if you want to learn more about all of the worlds that we know of outside of our solar system, you can go check it out on NASA's website. They have something called the New Worlds Atlas, where you can learn about each and every one of these exoplanets. So with that, I'm going to hand it over to Peter, who's going to cover how we get there.
All right. Yeah, how do we get there? This is actually far from easy. Liz, do you know the first rule of Space Club?
Is it don't talk about Space Club?
No, it's space does not cooperate. We learned this from Mark Watney, meaning if you do anything with space, better know really what you're doing. As a rule of thumb, you should be treating vacuum like a poisonous gas. That about gets it right, and then you can start building things. Actually, there's a second rule of Space Club.
Don't talk about Space Club?
No, be prepared. To quote Mark Watney again, yeah, exactly. And these are just some of the topics you want to maybe think about. It's not just about should we go at all, and if how, should we colonize, should we send robots? What propulsion is the right one? Do we need planetary bases on the way? What's this actually sociological aspects? Do we get along on those spacecrafts for many, many years in confined space?
I don't know. Would my husband get on a spaceship with me for 4 years?
So, meaning you have to plan your trip carefully. This is nothing new. Even if you do something within our solar system, you have to plan your trip carefully. People have done this before. Well, obviously, we have sent probes to the inner planets, to the outer planets before. And the first concepts date back to the beginning of the 20th century. This is actually the way, for example, how you want to get from Earth to Mars fuel efficient. It's a so-called Hohmann transfer orbit. So you start from Earth, which is the blue planet, in the position where it is, where the blue filled circle is shown on the slide. At the same time, when you start, Mars is in the position where the open circle is, but by the time you have then traversed on your Hohmann transfer orbit towards the Mars orbit, Mars will be in the right position that you can actually just land on Mars. If you have more time on your hands, if you want to use even less fuel, there are other options. We've just seen in the previous talk and heard about Rosetta. And Rosetta did several swing-bys and gravity-assisted flybys by other planetary bodies in our solar system. Using those to then accelerate, get into a different direction without using any propulsion. And actually, since a couple of years, there's another method which I encourage everybody who is interested in this to just Google and look up. This is the Interplanetary Superhighway, as it is called. This is a system of how you get from Lagrange points to other Lagrange points in our solar system without any fuel. Essentially, you just have to get onto those tubes, which are in math speech, I guess, open and closed manifolds. I'm not a mathematician, but this is what you want to look up. And then you can just coast along these lanes through our solar system. But normally you want it fast.
You mean like one of those SpaceX rockets?
Well, sort of. So SpaceX is fine for Mars, definitely. These are chemical rockets. You can still tweak them a bit, but if you really want to go far out in the solar system or then even talk about interstellar, then you have to use other methods of propulsion. Let's look at these very crazy spacecrafts for interplanetary missions, which have been proposed before. You will see these designs a lot if you start looking into spacecraft design. It almost always looks like this. So there is at the very front, there is the payload, which could be some crew compartment if you want to send humans. It could be some cargo which you want to send to a outer colony, maybe in the asteroid belt or to the moons of Saturn. The big thingy behind it, this is not wings. I mean, we don't need wings in space, but we need to get rid of a lot of excess heat that gets created by our nuclear reactor, which is at the very rear of our spacecraft. So these are radiators, and since space is essentially black and really cold, I mean, it's 2.4 Kelvin.
2.7315.
2.7. She's the expert. We can efficiently radiate hot stuff away using so-called radiators. At the very end, as said, there is a nuclear reactor. Of course, there are some things like ion engines and whatnot, but I want to highlight one of these crazy ideas, and this is how the reactor actually looks like. It's a fission fragment rocket engine. What you see is, like in a reactor, you might know it has some nuclear stuff in the middle, here shown in green, and of course there's a moderator around it to get the neutrons to the correct speed. What is the interesting part here is that you actually will use the propellant itself, so the plutonium carbide dust confined with superconducting reflector magnets to get the fission particles out and some radiation to the to your back. Of course, the particles have to be charged for that, so gamma radiation will go in the other direction, and you better have some shield there, because otherwise you are frying your crew. The fission fragments are pretty fast. They go at almost 2% the speed of light, and we also get a ton of energy out of it to power thermoelectric generators to have excess heat to get electricity on our ship. If you want to go to interstellar, this is not going to cut it. We have to have high specific impulse and high thrust. So we'll talk briefly about Project Orion. This is a complete different Orion than the
NASA Orion. This is the old Project Orion.
The old Project Orion. Not to be confused with Project Pluto. Don't look up Project Pluto. This is insane stuff. And after 10 clicks on the interwebs, believe me, I know what I'm talking about. I'm from Bielefeld. You end up in a swamp of conspiracy theories. Don't go there. Don't. Okay? So this is Project Orion, which is essentially nuke us to the stars. We have a payload section again at the very tip of the ship. We have a propellant magazine. And then we have a shock absorber at the very rear. And what we do, well, we take some nukes, which we have in our compartment, just throw them out of the rear, have them make kaboom, and then propel our ship forward.
I would like to point out that this is, I think, the most reasonable use of nukes, so.
It would be perfect reuse of our nukes today. Of course, you maybe do not want to have this on your surface body, maybe if you want to start from Earth or from Moon or from Mars, because, well, your mates who stay in the lunar base or so will essentially be fried because of your nuclear explosion. So do this in free space where there's nobody else, and see that there's nobody tailgating you or something. Watch out. Are there other options? Yes, there are other options. As said, there are these ion engines, which are very nice engines. They are being flown on spacecrafts right now. There you use an electric field to accelerate ions. It's only a tiny bit of thrust, but it's very, very efficient. And if you have a long mission duration, and you can just, I mean, a rocket, for example, like the Saturn V or the space shuttle, they go for some minutes, but if you have an engine that can just power you your craft for years, you will get faster in the end. About laser propulsion, we will talk in the next talk at the very beginning, and all the other things we'll not talk about, because as said, you get into a swamp of conspiracy really fast. Don't look up EM drives. Just don't do it, okay? The fairy dust would actually be some of the torch ships classified as normally constant acceleration engines, and this could bring you to the stars pretty fast, but we have no idea whatsoever what technology to use in constant acceleration drives. So if you're going fast, you have to have your shields up. Believe me, if you are going at 20% the speed of light in the end or something like that, you have to make sure that you understand that space is not empty. Space looks like this. So this means there's a ton of stuff between the stars, the interstellar medium. It's neutral atoms, charged atoms, molecules, dust. And if you do a quick calculation, you will see that if you, for example, go at a speed of 20% the speed of light, you will erode 1 centimeter of aluminium in front of your ship each year, just from the interstellar dust. So this is something you really should pay attention to. Of course, there are other things also floating around, micrometeoroids, although they are not that frequent in interstellar space. Of course, it's also something we have dealt with before, with interplanetary missions, with Earth-Moon missions, with things in Earth orbit. And this is, for example, how it looks like. This is a famous so-called Whipple sheet on the left. So you essentially have a sheet of metal in front of it, which absorbs the first impact, and then you just have a spray of debris from your impactor on your actual spacecraft. Or you could do something like metal foams or something. This is actual research being done right now. So yeah, we're preparing for that. But of course, we want to have really nice things, maybe, and then, yeah, it's BYOM, bring your own magnetosphere or force field. And yeah, if you, for example, just put a magnetic field around your ship, you could collect plasma on the way, have a nice plasma in front of you, and that would lead to having a nice magnetosphere around your ship, which would then deflect charged particles. Never forget what is behind you, because your own reactor is trying to kill you all the time. And that's actually why this thing has this wedge shape. This is not because the artist thought this looks nice. No, because this is the deadly radiation. And actually, well, it's a cone around your ship. So when you turn your ship over, because you have accelerated for 20 years in the one direction, and then you turn it over at the middle of the trip, accelerate in the other direction, because you want to decelerate, well, there should be nobody sitting in front of you, because your reactor is then pointing in that direction. The particles are still fine. You will not get your own particles, but everybody who is in front of you will then get the full radioactive blast.
So maybe point your ship slightly off of the planet you want to land on.
Yeah, maybe.
Yeah.
So still, with all of this, as said, the only option of going really fast are so-called torch ships, constant acceleration drives, which could bring us to Proxima Centauri in about, 7 to 8 years, ship time. Earth time would be about 10 years, because relativistic effects will then come into play. Anyway, it will take long. It will take so long that you better take a nap during the voyage. And this might seem a bit like science fiction, but actually this is research that is being done by medical researchers at NASA, at private companies right now, and these are artists' impression. Hibernation could be an option. It's now routinely used for people who have had severe accidents. You just cool the people down. And actually, if you, for example, cool down your body temperature from 37 degrees Celsius to 32 degrees Celsius, you're reducing your metabolic rate by 70%. And this means, well, you don't have to bring a lot of
water,
food,
oxygen
on your ship. Last thing, no, this is not space. Sorry, this is not an option. This is no option at all in space. There are so many things which have to work over a so long period of time that we actually, for some of those, have no idea how to accomplish this. We're talking about trip times of around 100 years, maybe. So I have not seen a computer that has worked continuously for 100 years. Neither a propulsion system, electronic system. So if you have such a ship, you better bring all the spare parts, and you have 2 ships, or you have maybe capabilities on board to do this.
Like mining asteroids to get new parts for your shield, which has eroded away.
Maybe that. But this is not to scare you away. This is just the challenges. I mean, we have done other things. Mankind has landed people on the moon. Soon there will be Mars. And please keep in mind, there's a very famous quote by the father of rocketry, Tsiolkovsky, and this is, "The Earth is the cradle of humanity, but no one lives in a cradle forever." So at some point we'll get out there. The question is when, but there's a lot of stuff to do, and you're all invited to take part in it. Thank you.
We have some time for questions left, so please go to the microphones if you have a question, and remember to keep it as brief as possible. Signal Angel, please give us the questions from the internet.
There's one question from the internet. If we assume EM drives will work and will have usable thrust, how would that change the space travel? Could we shorten the path instead of relying on parabolas?
Good question. Next question. Microphone 1.
If we have magic, then everything is fine, yes. Yeah.
I have a question that has always bothered me with space travel, and that's basically, what's the rationale behind aiming for a foreign and far away planet that right now is basically an utter wasteland, an hostile wasteland? And instead of finally getting our shit together as a species, like surviving on the planet that we were literally made for by nature, why should we survive on any utter wasteland if we can't do it here?
Well, if you remember earlier, there was the problem that our sun is eventually going to expand and consume the Earth.
Yeah, but that's
So
far away.
Yes, I'm not advocating for us not getting our shit together. We should definitely do that. But in the very long term, human space exploration is a necessity. And so we should always keep our eyes on the future of our species in general.
So one last question, microphone 4, please.
Can you think the Alcubierre drive will change everything?
Well, it's a nice mathematical concept, but the stuff you need to make it real is, it's not even clear if it's physical reality. Yes, if we have a warp drive, it's fine, yes, but sorry, it's not going to happen within our lifetimes, I promise you.
So if you manage to build a warp drive by the end of Congress, we take Zaltu with us.
Okay, so one more thing is that we've planned for the Space Track speakers to congregate shortly after midnight at the speaker's sofa outside of Saal G. So if you all have more questions for us that you would like to ask later, shortly after midnight, that's where we'll be.
All right, thank you.
Thank you very much. That was Liz George and Peter Bushkamp. Thanks.